spring break. I just want to talk to you for a second about what we're going to cover for the rest of the semester. So for the rest of the semester, we are covering basically all of chapter 4. I guess maybe not all of it. The first 6 sections, 6 out of 7 of the sections. So we're going to talk about exponential and logarithmic functions. And that'll be the what makes up the rest of the new material for the semester. Um, okay, so concerning the final exam, there are going to be some questions from earlier in the in the semester, covering material that was given earlier in the semester. And I'm going to be really explicit about what those will be. It'll just be one problem. In fact, I can just tell you real quick. Basically, what I have to do is I have to make sure that I'm covering so-called, no, hang on, sorry, student learning outcomes. So I'm going to scroll to those in the syllabus all the way at the bottom. So there are student learning outcomes for this course. Hang on. Okay. Which basically say what a student should, at the bare minimum, leave this class knowing how to do. Well, maybe it's not the bare minimum, but it's what a student should leave this class knowing how to do. And this is a way to measure your success in the course. So you should be able to solve quadratic equations. So there will be at least one of those on the final exam. You should be able to recognize the effects of vertical shifting, horizontal shifting, transformations of graphs, okay? So at least one of those on the exam. And then this last part concerns actually stuff from chapter 4, which we are going to start today. So basically the way the final exam is going to work is, if you ask me, is it comprehensive, meaning, does it cover everything? The short answer is yes, but really the actual answer is that there's just going to be one question about solving quadratic equations, or one quadratic equation, right? And maybe one or two problems recognizing these effects of transforming graphs. And the reason I might split it into two is because I could put all of it in one problem, all of these things in one problem, but that would make the problem pretty hard. It's easier if I would split it into two different problems and do like just vertical and horizontal shifting in one, and then this other kind of transformations in the other, instead of having it all together, because that can get that would get tough. So and then the rest of the final exam coming from stuff in chapter 4, which is what this would fall into, that stuff in chapter 4 as well. Okay, so are there any questions about any of that? Are there any questions about what's going to be on the final, or how the final is going to be given or anything? I can just go ahead and tell you that it's going to be given remotely. And it's going to be given, all of this is in the syllabus. The final exam is April 30th at 8 a.m. We can talk about that time if y'all don't want to take it that early. We would need to get everyone on board with taking it at a different time, because I can't just shift a final exam date. I can't do that unless every single person in the class agrees to it, because you might have other exams that day. So
I have a question.
yes, go ahead.
Are you gonna be current in like grades or anything like that?
Current in grades,
I said, are you gonna be curving grades?
curving grades. No, the curve. No, you mean like dropping stuff?
Or like, I don't know, like some teachers curve grades or something like that. You know what I'm saying? Like
I might. We'll see how it. Usually, exams. I mean, not exams. Grades are only curved if that only happens if every single student like makes like a C or lower. So that would just have to, I would have to determine that based off of the end grades. As of right now, that's not the situation. So, but typically curving grades are for, I mean, in my experience, curving grades happens when like the teacher teaches or whatever, you know, and then all the students take the course and all of the students do really badly. So then the instructor's like, well, it must have been me if every single student is doing poorly. So then they say, well, then, you know, I need to do something about that. So that would be something that I would have to determine after the, you know, final grades are in, or rather after I calculate the final exam and the final homework set and all that. But as of right now, I would say no. But again, that decision would be made at the end anyways. Yeah, so let's see, what else can I say about the final? The final is, I think I said, is given remotely, meaning you take it through HonorLock, which I think most of you have dealt with HonorLock, and if not, we'll talk about that as it comes up. Or as the time comes closer, I'll make sure everyone's on board with how to take it through HonorLock. And you can't miss the final. You know, for the other exams, if you here, let me pull this up. Let me show y'all. Let me show y'all here. So for the other exams, if you miss it and you reach out to me within 24 hours, then we schedule a makeup exam. For the final, though, you can't do that. Does it say that? I'm reading through this real quick. Okay, so I didn't write it explicitly, but I think it's somewhere else that you cannot miss the final exam. So you got to make sure that you're there for that day. Or not there, but you take the exam at the appropriate time. You won't be on campus, right? You're taking it remotely. Okay. All right. So let's go back here. Stop sharing. Flip my camera. Come on. There we go. Okay. So now that that's all out of the way, we can start chapter 4, which is exponential and logarithmic functions. So okay. So what we're going to do is we're going to spend the first 2 sections defining exponential functions. So 4.1 is just called exponential functions. So the way this chapter is going to work is we're given 2 new types of functions. Exponential and logarithmic functions. And we're going to spend some time talking about the functions. And then we'll talk about some of their properties and new laws that dictate how these functions act. And then we'll talk about modeling with them. And what modeling means is real life problems. So in fact, right in section 4.1, we'll do a little bit of real life problems with some compound interest stuff. So this chapter is really interesting because exponential and log functions are really interesting. They can be used to model, they are used to model all sorts of things in real life. They're used to model like growth of bacteria. They were used to model and extrapolate data for the COVID-19 virus, right? Like predicting how many people would get the virus and all that. Those are exponential functions doing that work there. They can be used to model how much money will be in a savings account or how much money you'll owe on a loan. growth of a population, right? Which I kind of already said. Also, even in chemistry, the decay of a radioactive substance. They can all these things can be modeled with exponential functions. And we'll learn in section 4.3 that logarithmic functions are the inverses of exponential functions, so they're going to come into play too. So anytime you're talking about modeling things with exponential functions, logarithms are going to be there as well. Just depends on the context of what kind of question you're asking, whether you'll want the exponential function or the logarithmic function. So let me give you an example, just a little example of what an exponential function or what exponential growth looks like. Let's say it that way. Growth. So we've already talked about linear functions. Linear functions, what does their growth look like? Well, it's like a straight line and there's a constant rate of change, right? That's a linear function. We talked about quadratic functions. We talked about polynomial functions in general, and they kind of, they look all sort of crazy, right? And we can use them to model different things. So what makes this exponential function different though? How is it different from a polynomial? And the way I'm going to answer that question is I'm going to model like a little kind of real world example, kind of made up like a little fake example thing. So let's say that we have some kind of, I don't know, bacteria or something. I don't know anything about biology, but let's say it's just some kind of like bacteria. And every hour it splits itself into two. So at time 0, we just have one of these things. So at t equals 0, we have one little bacteria thing. I don't know if this is the way bacteria reproduce. I have no idea. But let's just say every hour, this little green dot doubles itself. It splits in half. That's how it reproduces. So at time 0, we have just one of these things. Then we come back 1 hour later, and we expect there to be two of them because it's going to split itself and make two of these little bacteria things. Okay, or maybe we'll just call it a cell, maybe. Anyways, I hope that if any of you are biology majors or know this sort of thing, I hope it's not like triggering you if I call it a bacteria. That might be really wrong, I'm not sure. Let's say now in another hour later, so after 2 total hours, it's going to split again, but now there's 2 of them, so they each split. So they each split, and now there's 4. And then what if we said, let's do one more hour. Let's do one more hour, and then I'll pose a question. So after 3 hours, we come back, and each one of these has now split. So the first one split into 2, then the 2 split each into 2, so now there's 4, and now each of these is going to split into 2. And now there's 8. 8 little green dots. So what if I pose the question and I say, let's say dot, 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 and then over here, let's say after a whole day, 24 hours, how many green dots will there be? How many green dots will there be? Okay. Okay, so the way we figure this out is, well, we could just count it up, right? We could just keep this pattern going until we get to t equals 24 and see how many we have then. But you may already have a feeling for that this would be a huge number, right? So maybe there's a pattern that we can see back here that we can then apply to get all the way to t equals 24 instead of having to calculate it by hand, just repeating this pattern over and over again until we get to 24. So does anyone see what is happening here? Like, how could you describe how could you describe mathematically what's happening between each hour? You could say that they're doubling, right? Each time they're doubling. So from 1 to 2, they're doubling times 2. And then from 2 to 4, that's doubling times 2. And then from 4 to 8, that's doubling. So each time t increases by 1, these green dots are doubling. Okay. So what does the mathematical relationship look like here? Well, I could say that this first slot for t equals 1 is the same as 2 to the first power, right? 2 times itself, or just 2 times itself one time, right? And then when I double that, I get 2 squared, right? So each time I multiply by 2, that means I'm increasing the exponent by 1, right? So I'm doubling each time. I'm multiplying on another 2. So that means in this case here for t equals 3, I'm at t cubed. So this looks like a good pattern because 2 to the first is 2, 2 squared is 4, 2 cubed is 8, and that's getting that idea that these are doubling each time. It's containing that idea by saying that we're increasing the exponent on the base of 2 by 1 each time an hour passes. In other words, we're multiplying on another 2 every time an hour passes. Does it work for this first case, by the way? Well, what's anything to the 0? It's just 1, right? So it does work. 2 to the 0 is 1. So that little weird case where we just have 1 starting off with, that fits this pattern as well. So that means if I say ... and I let t equal 24, then the number of little green dots or little bacteria thingies after 24 hours, if they're doubling every hour, will be 2 to the 24th. Will be 2 to the 24th. Okay. And what is that? We can go ask the calculator. 2 raised to the 24th, and it's 16 million equals 16,777,216. So way more than I could have ever have hoped to draw, right? So this is the power of exponential growth. Things get very massive very quick. This is much stronger than polynomial growth. And we're going to look at an explicit example of why it's true that this is stronger than polynomial growth. But this is kind of just a quick example of a certain type of exponential growth. This is in particular for something that is doubling for each unit of time. In this case, I said hours. It could have been days. It could have been minutes, seconds, whatever you want it to be. It doesn't have to be time either. It's just whatever the input variable is measuring. For each unit that passes, the output is doubling. Since the output is doubling, that's why our little base number is a 2 in every case. And the number of times it doubles is up in that exponent. So let's compare. I told you that this is much stronger than polynomial growth, but let's see that in action. So first, let's define let's get an example of an actual exponential function down. So a function that can be used to model the previous example, is f of x equals 2 to the x. Okay, where x now is the thing that's changing, right? X is representing in the example I wrote down, the number of hours that passed. So notice that x, the variable x, is now, it's up in the exponent spot, right? The 2 is staying fixed, right? So let's real quick just do some practice with this. Let's just practice evaluating. So let's say, what is f of 3? F of 3. So f of 3 tells me to write my function, but everywhere I see an x, I put a 3. So f of 3 is the same as 2 raised to the third power, just using the function definition here. And then that is the same as 8 when I evaluate it. 2 cubed is 8. Okay. What about f to the 10th power? This would be 2 to the 10th. And that is the same, so I don't know that off the top of my head. I'll have to go to the calculator, hit and then that, and that. 1024. By the way, when you're plugging this into the calculator, it depends on what kind of calculator you're using. You'll either hit 2 and then the caret button, this little button, and then 10, or you might have to do 2 and then maybe it might be the x raised to the y button, and then 10. Okay, so that's how you calculate that, how you calculate these things in a calculator. Or maybe some calculators might have the button that looks like this, like the base number and then the little exponent position up there. That might be an option as well. Just depends on the calculator. Okay. Let's look at f of 30 now. Why not? F of 30, that's going to be the same as 2 raised to the 30. And then we'll use this to compare to a polynomial function. This gives me 1,073,741,824. So all I'm doing here is just showing you how to evaluate a specific exponential function. And you should just make sure that you know what kind of button you need on your calculator to be able to type this in to get this answer. So how does this compare to polynomial growth? How does it compare to a polynomial function? Well, let's name another polynomial function. Let's say, now polynomials, I could pick any sort of, well, polynomial is a broad class of functions, right? I can pick any sort of degree for the function. Oh, what should I pick? Let's see. I don't want it to be too crazy. Let's see, I'm playing with numbers. Maybe like a 5th degree. So let's let g of x, and just to keep things easy, let's just let it be x to the 5th. X to the 5th. Okay, let's evaluate this and see how it compares to the exponential function. So x to the 5th, that's a fairly large exponent. It's a fifth degree polynomial. We didn't do a whole lot with these other than just say, oh, it's odd, so it has this sort of shape and blah, 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 all that stuff, right? What does this evaluate to at these same three inputs? So let's look at that. So g at 3 is 3 to the 5th, 3 to the 5th, which is going to be, what is 3 to the 5th? So 3 to the 5th is, oh, come on, calculator. 81 times 3, which is 243. Oh, I should, let me write out what I'm doing here. This is 3 raised to the 5th. There we go, which is 243. Okay, so at an input of 3, it's beating the exponential function by a lot, right? The exponential function is only at 8. Let's look at g of 10. G of 10 is 10 raised to the 5th. Right, just plugging into the function. And 10 raised to the 5th, well, that's going to multiply 10 by itself 5 times, and that's going to give us 100,000. Or, yeah, 100,000. So at the 10 input, this function, this polynomial function is still beating the exponential function. Now, I told you that exponential growth is stronger than polynomial growth. So what is going on here? Well, let's see what happens at g of 30. We have f at 30 already. F at 30 is this 1 billion, blah, 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 blah. So g of 30 is 30 raised to the 5th. So notice how in each of my outputs here, the exponent is staying fixed, right? And it's the base number that's changing for this polynomial function. Compare that to this exponential function where the base is staying the same, but the exponent is changing. So let's now raise 30 to the 5th and see what we get. I'm getting 24,300,000. Okay, so at an input of 3, the polynomial function is winning. At an input of 10, it's still winning. But at an input of 30, once we get to 30, this is just has skyrocketed way beyond this polynomial function. The polynomial function is only at 24 million. It's only at it's not even at 100 million. And this thing is at 1 billion. Right? It's at 1 billion. So exponential growth, while it may seem like it starts off kind of slow, it eventually just is way, way faster than a polynomial function. So if we were to graph these, let's see what they look like. And we will talk about specifically the graphs of exponential functions as well, but let's just see what we're getting here. There's 2 to the x, and here's x to the 5th. So when I say that that one of these graphs is faster than the other, what I mean is that it gets taller faster, right? It needs less inputs from x to get taller faster. So we see that the polynomial function, the blue one, is stronger or faster right now. But if I zoom out, I mean, how far do I have to? This may have been a terrible example. Oh, goodness. Where does it beat it? Somewhere around, I'm on my laptop. Oh my goodness. This is a new laptop. I still haven't figured out how to use the little pad thing. Okay, never mind. Disaster. Backing out. At some point, it does beat it. Somewhere out here, I would have to go, I would think I would have to zoom out way too far. The numbers I picked were just too big. Somewhere at 30 is where our function beats it, but I would have to go all the way up to like 1 billion to be able to see that. So let's look at a smaller example. How about x squared? Where does it beat x squared? Ah, that's nice. So look at this x squared graph. For a while, x squared is growing a little bit faster, right? Or it seems to be. It seems to be stronger than the 2 to the x function, which is in red. But then eventually, right up here, the red function takes back over, and then the polynomial function will never catch it again. And the red function is just going to keep getting faster and faster. And the quadratic function, the polynomial, is never going to catch it again. And this is what's happening with the x to the fifth as well. It's just that it's happening at much higher numbers. So couldn't really show that because the numbers are just too high. It's too high even for it to be nice in Desmos. Okay. So I want to get into looking at some special inputs for these exponential functions, like negatives and stuff like that. Fractions, maybe. What does that stuff do as inputs? But first, let me officially define an exponential function. So we can have some terminology here. We say with base A, here's its domain. We say it's defined for all real numbers. That means its domain is all real numbers. Denoted by x, that domain variable being x as it usually is. And we say f of x is equal to a to the x. So we say its base is a, which I've already thrown that word around a couple times, but I hope that makes sense that we call the base a, and its input variable representing the domain is x, and its domain is any real number. But we do say something about a. We want a to be positive. If a is not positive, then we get into this nightmare where the thing is bouncing back and forth between positive and negative values for x, because if x is even, then the thing would give us a positive output. But if x was odd, then it gives us a negative output. So it ends up not being a nice, smooth function. It just bounces back and forth between positive and negative. So that's a nightmare we don't want to deal with. So we take a to only be positive. And also, so a can be any positive number except for 1. And the only reason we don't want 1 involved is because if it's a 1, then it's not an exponential function. Because note that, so why is a equals 1 not allowed? Why is a equal to 1 not allowed? Well, 1 raised to any number x is just going to be 1. This is not an exponential function. It doesn't represent that exponential growth where things are like doubling or tripling or it's not moving at all, right? It's just a solid 1 function, meaning it's a constant flat line. This is not an exponential function. We would call it maybe a linear function or a constant function. So 1 is not excluded because it like breaks the math or anything like the negatives would. It's just not allowed because it's not interesting, and we want to only include things that actually move. An exponential function should be moving, right? It should either be exploding upwards or exploding downwards, which we'll explore that as well. It should not just be staying stagnant. And a 1 makes it stay stagnant. Okay, so there's a definition for us. I've noted the domain, so let's just make a note that the domain is unrestricted. So when I say unrestricted, that means I can write it down as an interval like this. So for any exponential function, this is its domain. Okay. What about the range? So let's say as we as we practice evaluating different numbers in an exponential function, try to guess what the range should be. Okay. So I've told you that the domain is just completely like whatever you want to plug in, it accepts it. And why am I making a big deal out of domain versus range? Well, because we're going to be talking at some point about the inverse of these things, inverse of exponential functions, aka logarithmic functions. And if we want to talk about the inverse, it's really nice to know what the domain and range of the original functions are, so that when we flip them, we sort of have an idea of how the other function should act, because we'll know the other function's domain and range because we'll just flip whatever it was for the original class of functions. All right, so let's practice evaluating with some non-whole numbers, meaning like fractions and negatives and stuff, and let's see what happens. So example 1. Let's pick a new type of function. Let's let f of x equal 3 to the x. Let's just start with f of 5, and then let's do b is f of -2/3. And you know what? I don't want to go that hard right away. That's the book's example for b, but I want to slow down just a little bit. Let's do f of -1, and then we'll do f of pi, which is a irrational number. So that's interesting. But there's nothing to say that we can't plug that in. F of square root of 2 is another irrational number. And then let's investigate some more negatives. A, B, C. And let's see, how about f of, let's do a big negative number. Well, how about just -5? -5, that's fine. That's big enough. Okay, so let's evaluate each of these. Now, you can do part A probably in your head or by hand, just multiplying 3 by itself 5 times. Easier to just use a calculator, right? That's how probably most sane people will do it, unless you just know what 3 to the 5th is off the top of your head. These other ones, though, in particular the ones with irrational inputs, definitely we're going to use the calculator for. I am going to show you, though, that the best way to do these negatives and fractional numbers, the best way to deal with those is not asking the calculator, because we can do these by hand and get very nice, clean answers. First of all, f to the 5th, we've actually already calculated this, is 243. 3 to the 5th power is 243. When did we calculate? Oh, that was that polynomial example. Okay, anyways, it was a particular, I inputted 3 into the x to the 5th function. But anyways, in this case, it's the base is 3 and the input is 5. So this is 3 to the 5th is 243. All right, what about part B here? So I'm going to write this one out a little bit more carefully. F to the -1 is 3 to the -1 by the definition of the function. But recall the exponent rule. Does anyone remember what the negative tells me to do with this 3? The negative in the exponent position? Tells me to take the reciprocal of it. the multiplicative inverse. So this is 1 over 3. Okay, so an input of a negative value into my function still outputted a positive. I gave it a negative and it gave me a positive. Let's just keep that in mind. Okay, part C is f of pi, so that's 3 raised to the pi, which is just going to be a question of asking the calculator. And since we're going to have to ask the calculator in round, we'll say approximately, so we'll use the little squiggly equal sign because we can't get an exact answer for this. This is going to be some terrible decimal number. And I'm getting 31 point, we'll just go 544. 31.544 approximately. So anytime you have to use the calculator in round, that's an approximation. That's why I use that little approximate symbol there. I'm going to have to do that for part D as well, because f of square root of 2. Square root of 2 is another nasty irrational number. Oops, so I'm going to have to approximate it again, plug that into the calculator, and I'm getting 4.7, keep how many I kept 5 significant figures, so I'll keep 5 significant figures there. Okay, so far all of the outputs have been positive. That's definitely positive. This is interesting, inputted a negative and got a positive. These are just weird examples showing that you can input whatever kind of number you want, even irrationals, into these functions. But notice they're still positive. The answers are still positive. Now let's look at this negative fractional input, f of negative 2 over 3. That's going to be the same as 3 raised to the negative 2/3. So I should be careful here and think about what this means. First of all, this tells me to take the reciprocal, right? The negative up there tells me I need to do 1 over 3 to the 2/3. Just recalling my exponent rules, dealing with negative exponents. This is what the negative exponent tells me to do. It's 1 over 3 to the 2/3. So that's 3 to the 2/3 down here. The negative has been used up to flip it to the bottom. And then this is the same as 1 over, well, I remember from the very beginning of the semester that this is the same as the cube root. How do I know it's a cube root? Well, because the denominator of the exponent, fractional exponent up here is a 3, so it's a cube root of 3 squared. That 3 is the base staying inside there. And then that's the same as 1 over cube root of 9, which cannot be simplified. Cannot be simplified. But the point is it's still positive. When I say it can't be simplified, I mean you can't do anything, like you can't do anything else with the 9, right? You can't pull anything out. I can get an approximate answer for this if I want, but this is a nice clean way of writing. This is an exact way of writing this output here. Notice that it's still positive. It's still positive. All right, whoops. Now what about if I make the negative input even larger? So f of negative 5 is the same. F of negative 5 is the same as 3 to the negative 5th, which is the same as 1 over 3 to the 5th by that negative exponent rule. And then this is the same as 1 over 243. Still positive. So some notes that we should make. All of the outputs were positive. Let's compare these negative values. Let me get this piece of paper out of here. F of negative 1 gave me 1/3. F of negative 5 gave me 1 over 243. This is a much smaller number. So it seems like as the input gets larger and more negative, the output gets smaller and closer to 0, right? Like this fraction keeps getting chopped down over and over again, but it's just getting closer to 0. Does it ever cross 0? That's the question. So remember the bigger question at the top of this example was, can we figure out what's going on with the range? The output, what is the output? Is the output completely unbounded, just like it was for polynomial functions? Because polynomial functions exploded off to infinity and negative infinity. So do these exponential functions do the same? They definitely explode off to positive infinity. We know that. We've seen that. But what about to the negatives? So just for a few more examples, we already know that picking this same function, f of negative 1 is 1/3. We know that f of negative 5 gave me 1 over 3 to the 5th, which is 1 over 243. What if I do like f of negative 10? Well, that would be 1 over 3 to the 10. What is 3 to the 10? I have no idea. Let's go ask the calculator. So this, by the way, this is still the same function from example 1. It's this function. So now I'm giving it a negative 10 up in the exponent, which is flipping it to 1 over 3 to the 10. And 3 to the 10 is 59,049. So that is just super, super close to 0. In fact, as a decimal approximation, let me write these decimal approximations for you. You already know what 1/3 is. It's 0.3 repeating, right? It's like 33333. Shoot, 243. Inverted. This one is approximately 0.004. I'll just keep the first digit that's non-zero. And then 59,049 is approximately, oh boy, 0.1234. Okay, I'm just rounding to the first non-zero digit. So the first one is 0.33333. And then that's f of negative 1. Then when I get to f of negative 5, getting closer to 0, I get to f of negative 10, getting even closer to 0. And you can imagine if I keep increasing this negative value, it's going to squeeze closer and closer to 0, but it will never actually touch 0. So these will never, exponential functions, here we go. Can never have an output of 0. They can get extremely close, but they will never actually just give you a straight up 0. I mean, it can get just insanely, unimaginably close to 0, but never actually just say 0. Because you can't give anything to an exponential. You can't raise a number to some other number via like the exponent operation and ever expect to get a 0, right? That's just not how the math works. So the range then of exponential functions is 0, but not including 0, and then off to infinity. Now, the caveat here is that this is for functions that have not been like transformed, right? I can take an exponential function and flip it around, flip it over the x-axis, and that flips all this on its head, makes everything negative, and it'll never touch 0 from the bottom, or I could like shift it down. So let me make a note about that. This is for these two facts are true. Oops. That have not been altered. So there's no like stretching or shifting or flipping over the x-axis or y-axis or anything like that happening here. It's it's for exponential functions that have not been altered. So for instance, like f of x, here are some functions that will behave this. Maybe f of x equals 2 to the x, f of x equals 3 to the x. We already know these behave that way. Anything of this form, right, where, as I said before, where a is greater than 0 and a is not equal to 1, right? But as soon as you start messing with the exponential function, and what I mean by that is like you take the exponential function, and if I do something like this, f of x equals 2 to the x plus 1, now that just throws a wrench in this idea that the range is bounded. That lifts the whole function up, right? So that scoots things around. So these facts are not good for this function. Another example might be this, if I put a negative on the outside of it, because that flips the whole function upside down, right? So the facts that I wrote about the range being 0 to infinity are only true for exponential functions that have not been shifted or stretched or flipped. Now, this should give us an idea of what exponential functions are going to look like. And let's go ahead and see what they're going to look like. Here we go. Scoot down. So here's the graph of the exponential function 2 to the x, which I've already shown you, but now let's actually investigate this range issue. So we see that the range seems to be unbounded in the positive infinity direction. It does not seem to like it's ever going to reach a limit with how high it can go. But look at how low it can go. It's never ever going to go below. Let me highlight the graph. It's never going to go below 0. In fact, it'll never touch 0. No matter how far I go out on the negative x-axis, it looks like it might be touching the x-axis, but if I zoom in, it still looks like it might be touching. Keep zooming in. Keep zooming in. Eventually, I'll see that it actually is not. Oh, there we go. Look at the scale that I had to zoom down to I'm down to the 10 to the negative 10. So this is, we're at like all the way out to the 10th decimal place to be able to see that these actually, in fact, it still is in fact above the x-axis. So see here, the points here, the input is about negative 35.678, and the output is just this super tiny number, 1.819 times 10 to the negative 11th. The times 10 to the negative 11th means you would literally write 0, 0, 0. You would have 10 zeros before you got to the 1819. So a super tiny number. Okay. So this sets us up to talk about the graphs of exponential functions in general. Where are we at? 5 minutes? Yep. So, yep, we'll save that for next time. We'll talk about the graphs of exponential functions and also need to talk about that compound interest, and that'll finish 4.1. All right, you guys are good to go. If you have questions, stick around and ask them. Otherwise, I'll see you Wednesday.